Learn more about anatomy in the Marine Animal Lab.
Unlike many undersea hunters, the octopus relies almost entirely on its vision to find and catch prey. For this reason, the octopus's eye is highly developed and can probably see images nearly as well as a human eye can. Much of an octopus's brain is devoted to interpreting the many signals coming from the octopus's eyes. The octopus eyeball is flattened like a fish eye. To focus on an object, the lens of the eye moves rapidly back and forth. The eye of an octopus is also quite large, making it easy for the octopus to see well at night when it does most of its hunting. Octopuses have strong beak-like jaws that are so powerful they can crush the shells of very large crabs and lobsters. When an octopus captures its prey, it holds the animal in its mouth, then kills or paralyzes it with a poison that is secreted by the octopus's salivary glands. The octopus then injects into its prey's body a digestive enzyme that dissolves many of the animal's toughest body tissues. Once the animal's body is soft enough, the octopus sucks it into its mouth. Because the octopus dissolves most of its food outside of its body, it only needs a simple digestive system to absorb food into its bloodstream. A few hours after an octopus captures a crab or lobster, all that's left is an empty shell. Unlike many undersea hunters, contrary to what many people think, sharks have excellent eyesight. A shark's eye can see well during the day and also at night when many sharks feed. Sharks' eyes are built very much like human eyes, except that they are much thinner. The shark eye is composed of 3 chambers: an iris, a lens, and a retina. The size of the eye depends on what kind of shark it is and where it lives. Sharks that live in shallow waters where there's plenty of light have smaller eyes. They don't need to capture a lot of light in their eyes to see. Sharks that live in deeper waters, such as the mako shark, have much larger eyes to capture as much light as possible. To help see in very dark water, sharks also have a special reflective lens that is located at the back of their eyeball just behind the retina. This lens acts like a mirror, reflecting small amounts of light in the shark's eye many times over. It is believed that most sharks see in black and white, but it's possible that a few sharks also see in color. Ears are not found on the outside of sharks or on any other fishes. However, sharks still have very good hearing, particularly for low-frequency sounds like those made by struggling fish. The shark's ear consists of a small membrane of skin that is attached to a spot near the top of the head. This piece of skin moves every time there is a vibration in the water. Shark brain. For many years it was thought that sharks had simple primitive brains. Yet recently scientists have shown that many sharks have large capable brains, especially when compared to other vertebrates. Certain sharks have even demonstrated the ability to learn simple tasks. A shark's brain is the center of a complex system of nerves and senses. Millions of tiny electrical messages are transmitted to the brain from all over the shark's body. For instance, the shark's eyes are constantly sending information to the brain about what is visible to the shark. Electrical sensors in the shark's face transmit information about the electrical fields being created by other animals in the water. At the same time this is happening, the shark's brain is sending messages out to the different parts of the body, instructing them what to do. Brains differ greatly in size and complexity from one shark species to the next. Large, fast-moving sharks like the hammerhead and dusky shark have bigger brains, probably because they spend more time hunting and tracking prey. Slower, bottom-dwelling sharks, which find most of their food in one place, generally have smaller brains. Shark brains are divided into 3 large segments: a forebrain, a midbrain, and a hindbrain. Each of these segments is responsible for controlling a different part of the shark's bodily functions. A lobster's eye is located at the end of a long, movable stalk. The eye has a hard, curved surface that is made up of thousands of tiny lenses. Each of these lenses acts like a separate eye, detecting differences in light and dark. Some lobsters are capable of seeing certain colors, such as blue and green. Because the surface of a lobster's eye is so large, lobsters see movements over a very wide angle, like the wide-angle lens of a camera. Lobsters are probably able to make out the forms and shapes of different objects. Lobsters have simple brains. A lobster brain consists of a dense collection of nerves called a ganglion. The ganglion sits at the end of a long string of nerve fibers that connect the brain to the rest of the lobster's body. The combination of the brain and these long nerves is called the central nervous system. As with other animals, the lobster's central nervous system transmits tiny electrical messages between the different parts of the body and brain. For instance, nerves in the lobster's legs, eyes, and shell are constantly sending messages to the lobster's brain about its environment. The brain, in turn, sorts through these messages and reacts automatically to those messages requiring some kind of action. This type of response is called an instinct, because the lobster doesn't actually think about the action before doing it. If the lobster's eye sends a visual message to the brain, say that a fast-moving object is approaching, the lobster's brain might respond by sending an electrical message to the tail, telling the tail to close rapidly and propel the lobster to safety.
Sea lions have excellent vision, both under and above the water. Vision is important to find fish in the water and to see enemies, such as people, above water. People sometimes hunt sea lions since these aquatic mammals love fish, and fishermen are afraid they eat too many. Today, most sea lions are protected by laws. After diving 40 or 50 feet deep, the air in the sea lion's lungs becomes completely collapsed from the water pressure, and the sea lion relies entirely on oxygen stored in its blood and muscles. The sea lion also uses its lungs to cool off. By panting, it releases hot air that would otherwise build up in its body. The column is the support of the body and often has shells and bits of algae stuck to it. When the anemone is disturbed and the tentacles are folded into the top, the shells make the animal hard to see on the rocks. It also helps keep the anemone from drying out at low tide when the seawater is not covering the animal. The throat and stomach of an anemone serve to circulate water for breathing, removing wastes, and for digesting food when it is brought in by the tentacles. Any food that is not digested, like bones or shells, must be tossed back out through the mouth. Radioles are the main branches of the fan worm's fan. They hold the fan up into the water so it can collect particles from the sea. Little hair-like cilia constantly beat to draw the water through the fan. The mouth of the fan worm receives a stream of mucus filled with microscopic particles of food that have been gathered by the fan-shaped radioles and pinnules. Only the smallest particles are retained for food. Vision is generally poor in whales, but gray whales often stick their head up out of the water to look at the coastline. It is believed that they can recognize landmarks on shore like mountains and remember them to navigate the same route next year. Whales have large lungs to obtain oxygen from the air, but they exhale much of the air before diving. In a deep dive, the lungs are completely flattened and very little fresh oxygen is available to the whale. Instead, it uses the oxygen stored in the muscles and blood. The outsides of many sea stars are covered with small pincers on stalks. These protect the star by catching little animals trying to invade its skin. The stalks are concentrated around the large spines in the skin and also help keep the skin gills free of debris. The sea star has a large stomach that can be extended outside its body. After the star has pulled open a clam or mussel, it extends its stomach out of its mouth and between the clam shells to digest the unfortunate clam. A sea star will take hours to digest a clam dinner. The distinct rings in the shell represent years, like rings on a tree stump. This allows scientists to determine the age of the clam. In this case, the clam is 5 years old. Clams have a muscular foot that allows them to move about the bottom if they are not attached to a rock. Clams that live in sand and mud have a larger foot. It is pushed out the opening in the shell into the soft bottom. Water is pumped into the far end of the foot to expand it like a fleshy anchor. Then the clam pulls itself through the mud. By repeating this process, the clam can move deeper when danger threatens, or rebury itself if it is exposed. Next time you dig up a live clam at the beach, put it on a sandy or muddy bottom in calm water and watch it disappear. For a long time, it was thought that dolphins had poor eyesight. However, they can jump from the water and take small objects from a trainer. This certainly testifies to their good eyesight. In nature, it is more difficult for the dolphins to see because the water is usually not very clear. So in nature, the eyes are probably less important than the dolphin's famous sonar. Dolphins have relatively large, well-convoluted brains indicating a degree of intelligence. It is known that dolphins have signals and a rudimentary language. Much of the brain specialization may be related to the sonar capabilities, since bats, which also use sonar, also have relatively large brains. The large eyes can detect changes in the angle of the sun. This means sea turtles can migrate long distances over the open sea with only the sun and moon to guide them. Baby sea turtles climbing up through the sand right after hatching can recognize the horizon of the ocean even though they cannot see the water. The turtle's heart is four-chambered like those of mammals and birds, but the chambers are not completely separated. Blood returning from the lungs is partially mixed with blood returning from the body. When the turtle dives deeply or is sleeping on the sea floor, its lungs are flattened from the water pressure. But that does not stop the turtle because with its connected heart chambers, its blood can continue to circulate without going to the lungs. Jacks have large eyes and good vision to see small fish and squids in mid-water. Jacks often herd schools of small fish into tight quarters and then slash through them to wound and injure them. They then pick off the fish that stand out from the school because they are wounded or got separated from the protection of the school. The heart of a bony fish is just under the gills. Blood is pumped through the gills to pick up oxygen before going out to the body. After going through the body, the blood, now low in oxygen, returns to the heart to be pumped up through the gills again. The gills are finely divided into many very thin-walled filaments. They look red because they are filled with blood that is getting rid of waste, giving up carbon dioxide, and picking up oxygen. The gills are designed so that the flow of blood on the inside of the thin skin is in the opposite direction of the water flowing on the outside. This counter-current flow makes it easier for substances to be exchanged between the water and blood. The gills are the lungs of the fishes, but they are also used for getting rid of waste products and balancing the salts in the blood.